Have you ever stopped to wonder how we can just perfectly predict the motion of literally anything in our universe? I mean, whether it's a sports car slamming on its brakes or a stone being dropped from the top of some ancient medieval tower, the universe actually plays by this incredibly simple, beautifully predictable set of rules. Welcome to this explainer. Today we're going to unlock what I like to call the master keys of motion. By using just a handful of simple math equations, we can figure out exactly where an object will be, how fast it's going to be going, and exactly how long it'll take to get there. It's almost like magic, but it's just math. So here's our roadmap for the explainer today. First, we'll hit the master equations, then translating math to asphalt. After that, it's the reaction time reality, followed by motion under gravity, and we'll wrap the whole shebang up with the tower drop. We're going to master the horizontal rules of cars first, and then we completely rotate our perspective 90 degrees to tackle gravity. All right, section 1, the master equations. Let's dive right in and set up our foundational rules. And hey, don't worry, these aren't meant to be rigidly memorized like some dusty old textbook. Instead, I want you to really think of them as a universal toolkit. So these three master equations absolutely beautifully condense all the complexities of motion. They govern uniform acceleration using just a few key variables. We've got initial velocity u, final velocity v, constant acceleration a, total displacement s, and of course, time t. If you know just a few of these, you literally hold the keys to unlock all the rest. Really, it's not about memorizing a random sequence of letters and numbers. It's about realizing that velocity, distance, and time are all fundamentally locked together. They're a package deal. But before we hit the road, we really need to clarify two concepts that are super easy to confuse. Displacement in time t is the total cumulative ground covered. Think of it as your entire road trip from start to finish. On the flip side, displacement in the nth second is the specific distance you covered during just one isolated tick of the clock. It's like asking, hey, exactly how many meters did you drive during the 8th second of your trip alone? Separating the whole journey from just a single snapshot is absolutely critical for solving these complex motion puzzles accurately. Okay, moving on to section 2, translating math to asphalt. Let's see how all this builds when we shift from abstract algebra to relatable, real-world horizontal scenarios. Let's put some tires on this math. Imagine an accident investigator trying to piece together exactly what happened at a crash scene. This is exactly how they do it. Take a scenario where a car starts entirely from rest. That means our initial velocity, or u, is exactly 0. Let's say it accelerates at a constant 2 meters per second squared for 10 seconds. By just plugging this into our displacement equation, that whole initial velocity part completely cancels out, because, the car started at 0. So we're simply left calculating half of 2 times 10 squared. Bam! Instantly, we know the car traveled exactly 100 meters. The math seamlessly maps right onto the asphalt. But what happens when the actual physical realities of the car change? Thanks to Newton's rules, we know acceleration is simply force divided by mass. So if the car suddenly becomes twice as heavy, maybe you loaded up a ton of bricks, while the engine force stays exactly the same, the acceleration gets cut exactly in half. A car that initially covered 18 meters in 3 seconds is now only going to cover 9 meters in that exact same time frame. These real-world physical changes instantly and perfectly alter the acceleration variable inside our master formulas. Which brings us to section 3, the reaction time reality. Up until now, we've been dealing with perfect math. But now, we got to introduce the imperfect delay of the human brain into our perfectly mathematical universe. Picture this. A driver is speeding along at 72 kilometers per hour, which, by the way, translates perfectly to 20 meters per second. Suddenly, the traffic light turns red. Now our math has to be split into two very distinct physical phases. Phase 1 is the 0.5-second reaction window. The driver's brain registers that red light, but their foot hasn't actually hit the brake yet, so the car is still cruising at a constant speed. Phase 2 is the braking window, where the brake pads finally engage and the car begins a constant deceleration right up until it completely stops. During that tiny half-second human delay, traveling at 20 meters per second, the car actually coasts a full 10 meters down the road with 0 braking. Just think about that for a second. Once the brakes finally engage to apply a deceleration of, say, 4 meters per second squared, it takes another 50 meters for the car to come to a complete halt. So the total distance? 60 meters. If the traffic light was 70 meters away, the driver stops with a safe 10 meters to spare. It's just a really vivid reminder of how far a car actually travels before you even start to stop. All right, section 4, motion under gravity. Now I want you to prepare for what I call the turn. We're going to rotate our entire mathematical perspective 90 degrees and face the sky. So here is the absolutely crucial point. Our master equations do not change at all, not one bit. The only thing that shifts are the specific variables we're plugging in. In the horizontal world, the car's engine dictates the acceleration, A, and our distance is just a horizontal line on the asphalt, S. But in the vertical world, Earth's massive gravitational pull completely replaces the car's engine. Acceleration becomes negative g, that's our constant downward pull, and our distance s simply becomes height, h. You can kind of think of gravity as this relentless, invisible hand that's just constantly pushing downward. Whether a ball is traveling up into the sky or falling back down to the earth, that acceleration of gravity never ever stops acting on it. Because it always pulls down, it slows an object on its way up, literally stripping away its velocity. And then it speeds the object right back up as it plummets back down. Let's imagine launching a ball straight up into the air at 50 meters per second. Gravity basically steals roughly 10 meters per second of that speed every single second. So after 1 second, it's at 40, then 30, then 20, then 10. And finally, exactly 5 seconds later, its velocity is 0. It just hangs there in the air for a tiny fraction of a moment at a height of 125 meters before gravity yanks it back down. This is such a vivid demonstration of the perfect mirror-like symmetry of vertical flight. And that brings us to section 5, the tower drop. This is really the climax of our explainer. We're going to tackle that classic physics scenario of dropping objects from grand architectural heights. When we actually compare these two scenarios side by side, it's wild how it reveals just how beautifully symmetrical these kinematics equations are. Throwing a ball up to find its maximum height relies on the exact same principles as dropping a ball from a tower. I mean, when you drop a ball from a grand height, its initial velocity is exactly 0, right? And because the rules of motion don't change, the time it takes to hit the ground and the speed at which it impacts are entirely predictable reflections of throwing it upward. Whether you're working from the ground up or the tower down, the master keys just fit perfectly into the locks. So we've seen how these rules dictate both the asphalt and the sky. But before we go, I want to leave you with a little unsolved puzzle directly from our source material. Imagine a passenger who just barely missed their train. They're standing on the platform, sadly watching the next to last car take 6 seconds to pass them, while the absolute final car takes 4 seconds to pass them. Assuming the train is accelerating at a constant rate away from the station, just exactly how late was that passenger to the departure? I challenge you to take these master keys of motion we unlocked today and apply them to the physics of this everyday life puzzle. Keep wondering, keep calculating, and I'll catch you in the next explainer.